So, okay, so where we are? We have converted our n queens problem into the local search formulation. We have defined a state, all queens on the board, one in each column. We have defined a neighborhood function, move a single queen to another square in the same column, and we have defined a optimization function, the number of pairs of queens that are attacking each other. And now we are interested in finding a state which minimizes this objective function. And let us come up with some really trivial algorithms, like really trivial. Okay. There are two trivial algorithms that I would like to suggest. Just randomly sample a new state. If I suggest this solution, this algorithm, what would you say? It's a good algorithm or a bad algorithm? Randomly sample a new state means take the first queen, randomly put it in the first column, take the second queen, randomly put it in the second column, take the third queen, randomly put it in the third column, and so on and so forth. Do you like this algorithm? Okay. Can you think of, if I keep doing this again and again and again, can you think of one good property this algorithm has? In the limit of infinite sampling, what is going to happen? I may find a solution. Do you see that? If I keep doing this, if I keep doing this, keep doing this, keep doing this forever, at some point by chance, I will hit on a solution to the problem, right, on an optimal solution. So, we call such an algorithm asymptotically complete. There is another algorithm which is in the same category, slightly harder to analyze, and that is will be called random walk. So, in random walk, what would I do? I would start from a state, I will look at my neighbors and then randomly jump to any one of the neighbors and not do anything else, then repeat. Then I am on that state, I randomly look at my neighbors and jump to any one of those neighbors, and I just keep doing this, that is it, forever. This is like Brownian motion in search space, local search space, local neighborhood space. I am at a state, I look at the 56 states where I can move queens, I just randomly move a queen and then move there, then repeat the process. It is possible that I even come back to my original state, but it is possible that I keep going and I just keep doing this forever. Even this algorithm is asymptotically complete, because at some point while moving around in the search space, I will hit the state which is the solution, as long as my neighborhood space is all connected. It should not happen that in this neighborhood space I can't have any edge to that that set. There is a chasm in the middle, you can't go from this to that, there is a separator, right. There should be only one connected component in my search space. So, that is an important property of the neighborhood function you define, that it should only have one connected component. You can technically go from any state to any solution to any solution in as many number of steps you want. So, these are two trivial algorithms: randomly sample and keep doing this, or randomly walk and keep doing this, and both of them will finally hit the optimal solution someday. But of course, we do not like these algorithms, and the reason we do not like these algorithms is because they will be too slow to be useful in practice. And today's goal, and the goal of these lecture slides, is to actually be useful in practice, right. We are slowly making the leap from optimal algorithms towards useful algorithms, right. So, now there is a very simple fix that starts to become useful already. Think about one of these algorithms and make a small change that leads you to a better algorithm. Somebody who hasn't spoken so far. There is a small change you need to do in one of these algorithms so that it starts to model your intuitions and become better. Yes, what is your name? Ashraya. Yes, Ashraya. Some sort of acceptance criteria in random walk, very good, you are almost there. See, notice that with every state I also give you the objective function. Now think again, I am at a state, I have neighbors. In random walk I move to a random neighbor, but what else could I do so that it might be slightly better? Better, you need scores for better neighbors, but don't you already have that? You are already given an objective function for every state. Sukriti, is it like this greedy search? Yeah. What is greedy search? Let's first make sure we understand the meaning of greedy. Greedy search simply says I have many alternatives, I choose the seemingly best and I keep moving, that is greedy. So anything that does this is some kind of greedy by definition, and yes, this is also greedy. In fact, greedy will be in its name. So what Ashray almost said is that an alternative algorithm would be something like this. I am at some state and I have lots of neighbors. For each neighbor I have the objective function. I pick the neighbor with the best objective function and I jump to, and I jump to that neighbor and I keep going. Everybody with me? Everybody with me? Any questions on this? This is important. This is the fundamental algorithm for this set of lectures. Then we will build upon it and we will do even better. But make sure you understand this bit. So, the bit is I am at a solution, I am at a state, I look at all my neighbors, I evaluate all my neighbors. Now, notice I do not want too many neighbors because then even one evaluation will be too expensive. So, therefore, 56 neighbors was okay, but 8 to the power 8 minus 1 neighbors is not okay. So, I evaluate all my neighbors and I compute their objective functions and I pick the best neighbor. Now, I can jump to the best neighbor, but I also need to have a termination criterion. And what might be a good termination criterion? Yes, yes, somebody at the back. What's your name? Vidit, yes, Vidit. None of the neighbors have higher objective than me. If all my friends score less marks than me, then I don't want to be like them. Bad example. But if any one of them scores better than me, then I want to be like them, so I become them. That is sort of what this algorithm is saying. Okay, modulo the joke. So the algorithm says if value of my neighbor is less than equal to value of the current, this is in the optimization world, maximization world, then return myself. If all my neighbors are worse than me, return myself, this is my solution. If however one of them is better than me, then move to the best neighbor and repeat. And you can convert it into min version by taking all less than equal to and making it greater than equal to and taking all max and making it min. So, that is it. And this algorithm is called hill climbing or greedy local search. Questions, this is the base algorithm with which we are going to start with. Yes, what is your name? Vedant, yes. Okay, good question. Should we not say less than? Okay, we can say less than. I agree. We can say less than. Now, you will understand it better in a few slides why less than equal to might be better in some cases, but for the purpose of the basic algorithm, let us say less than. Okay, good. What else? Okay, good question. What's the name? Path. Path says, do we need to calculate all the neighbors and pick the best, or can we just find one first neighbor which is better and move? These are two versions of the same algorithm, right? There are many versions that you can create, and I hope that for your assignment you do create. different things work better in different situations. For example, if my neighborhood space is very large, then evaluating all of them and going to the best, or finding the one better one and moving there, which one will be better? The finding one better and moving there, right? So, some of it will depend on how extensive your neighborhood space is, right? These are fine algorithms. There was another question. Yes. Yeah, wait. So, where would it get stuck? We'll get to that. That's exactly what we'll discuss today. So, give me a few minutes. So, the suggestion is that it might get stuck. Vidit, right? Vidit says it might get stuck, and we'll talk about it in a minute. So, let's first make sure we understand this. So, what is hill climbing search? Hill climbing search is that you look at the peak. You want to reach the peak. You are somewhere in the bottom. You look at all the places you can go, and you just maximize your elevation towards the top. And the hope is that at some point, if you keep doing this greedily, you will hit the peak. That is sort of what greedy hill climbing says. There are some interesting characteristics of this algorithm. Hill climbing does not look ahead of its neighbors. It does not care. It just looks at its neighbors and takes a move. Looks at its neighbors, takes the move. Looks at its neighbors, takes the move. Does not look beyond its neighbors. In that sense, it is so different from depth first search and breadth first search. Think about how depth first search did. If you think of it as local search space, it first goes to its neighbor, goes to its neighbor, goes to its neighbor, but then backtracks. None of that. I've forgotten. I don't even know where I came from. It has no uncertainty built in, no notion of randomness built in, except if there are many best nodes. If I have many best nodes, then it will take the best among them, anyone randomly among the best ones. So, a beautiful way to think about hill climbing is that you are trying to climb Mount Everest in a thick fog with amnesia. And then you will say, why? If a human was doing it, would we call it an intelligent algorithm? And we'll talk about that. But let's make sure we understand this analogy. It's a beautiful analogy. By the way, do you know how much traffic there is on Mount Everest these days? It's terrible. Apparently, there are kilometers of queues of people trying to go up to the peak. Very, very sad. And none of them are trying to climb Mount Everest in a thick fog with amnesia, because all of them have a Sherpa or someone who is taking all their luggage and taking them with them. So, they are just following blindly, right. It is sort of blind following, not even blind search. So, but coming back. So, we are trying to climb Mount Everest, we are trying to get to the peak, we have fog. What is the semblance of fog here? What is the analogy? I can only look at my neighbors. I am extremely myopic. I can't look even beyond one step beyond my neighbors. The visibility is too bad. I can only look at my neighbors and I have to make the best move possible. And why amnesia? I have no memory why I am here. The only thing I know is I am here. And why climbing? Because at every step in my neighbors, I pick the best, the maximum value. That is why climbing. Okay? So, each of these words have actually an important meaning, except Mount Everest is for effect. Right? So, this is our point of algorithm. Now, we come to Vidit's question, is it going to be optimal? And in order to understand this, let us look at this diagram, and this diagram is going to show you what is going to happen. Do you think that if you were doing hill climbing, even in this simple 1D, 2D diagram, you would get to the global optimum, the global maximum? Can you get to the global maximum? The question is depends on where you start. So, if you have good genes, then you can be super successful in life. Lots of people didn't get the joke. They are thinking seriously, is it really? That means I have no hope. But it does matter, right? You can't argue that it doesn't matter. There is a big nature versus nurture debate, and there is lot of, I used to be a vehement nurture supporter, but over time I have toned down. I feel that nature has something to offer in life. And in fact, believe it or not, we will talk about nature and natural selection and all of that towards the later part of this set of slides, in this class itself. There is a major connection with natural selection in local search. But since I am getting out of time, I want to quickly explain this. So, what can happen is that if I start here, right, then I could be stuck in a local optimum. And my greedy hill climbing will stop here, it will say all my neighbors are worse than me, and so what do? Well, I stop and I will return the solution, but that will not be the good solution. It is possible that I start here and at some point I reach this shoulder, and that is where there was a question, less than equal to or less than. If I say less than, then I stop at the first point in the shoulder. If I say less than equal to, what happens? I can keep moving up, I can keep moving flat on the plateau, and then at some point I hit this point possibly, and then I can start going up. This is called a sideways move. We will come back again. And the other interesting thing that you have to realize, and maybe that is when we will come back to, that if I am at a local maximum and if I want to go to the global maximum, what do I have to do? I have to first come down the hill. If you are at a chota hill, a tiny hill, and if you want to reach the Mount Everest, what first thing you have to do is come down that hill. You can't be standing as the king of the hill and hoping to achieve at Mount Everest until you come down and become a commoner. So, we will talk more about that, the beautiful philosophical analogies, but for now we will stop at the fact that hill climbing is possibly a good algorithm. We do not know that yet, we have to explain that, but it gets stuck in local maxima, and so we need to fix that, local maximum, local minimum, whatever, and we need to fix that too. We will continue from here in the next section.